linear measurement. And the first thing we need to talk about is we talked about lines yesterday. Hold on. So we talked about lines, and we said that a line is an infinite string of points. And it's infinite in two directions. Okay? Because it's infinite, it has no length. We can't measure infinity. So we cannot measure lines. Not true lines. What we can measure is a line segment, which is a finite piece of a line. That has two endpoints and can be measured. So infinite means goes on forever and ever. Finite just means it ends. We want to talk about metric units first. We have millimeters, centimeters, and kilometers are most often used. But you also have decimeters, decameters, and hectometers, but we don't use those often. It's base 10, which means that there are 10 millimeters in every centimeter. Then there's 10 centimeters in every decimeter, 10 decimeters in every meter. Oh, I forgot meter. Then 10 meters in every decameter, 10 decameters in every hectometer, and then 10 hectometers in every kilometer. So every time you go up a unit, there's 10. It's going up by 10. Which means that a millimeter is equal to a decimal place in a centimeter. So it's a tenth of a centimeter. So what I can do is when I look at this 4 centimeters, the big lines are the centimeters and these little lines are the millimeters. So this is 4 centimeters. It's nice and even. When I come over here, I'm not on a perfect centimeter, but I don't have to deal with fractions because each little line is a tenth. So it didn't copy well, but I think that's 0.4 or 4 millimeters. So I can say that's 4.4 centimeters. Or if I wanted to measure it in millimeters, it would be 44 millimeters because this would be 10, 20, 30, 40, and then 4 more. Metric's nice that way that everything works out to be like the decimal places of each other. Here I've got 5 centimeters and it looks like 2 millimeters. So that would be 5.2 centimeters, or I could say 52 millimeters. Okay. The biggest mistake I ever see anybody do is line up the end of the ruler and start measuring from there. But as you can see, 0 is actually like off of the end. So you want to start measuring at the 0, not at the end. Okay, so just be careful of that. And it makes a big difference. So if I measure this dollar bill in centimeters, if I come from the 0, I'm at 15.5 or 6. 15.6. If I'm in the wrong place and I measure from the end there, I'm doing 15.2. That's a 4 millimeter difference. So always be sure to line it up with the 0. Okay, so we did that. So that gives us 15.2 centimeters. Okay, if I want to measure the length of a pencil, first have to find one. Okay. And we're going to do the best we can. I mean, obviously you can see that the, you can't see because I don't have this up. You can see the eraser's kind of chunky, so it's hard to tell, but you do the best you can to line up the eraser to the 0. And we're doing millimeters, so we're at 16 centimeters, and then it looks like another 2 millimeters. Well, 16 centimeters is 160 millimeters, so this would be 162. And so in English Standard we have inches and feet and yards and miles. And unlike centimeters where you have the millimeters, which make nice decimal places, inches use fractions. So we're going to have to use fractions on these. Now, between the 1 and the 2, the halfway point, that's 1.5. And then after that, that's way too fast. The halfway point between the 1/2 and the 1, that's 1/4. So this would be 1/4, 2/4, 3/4. Okay. And then halfway between a 1/4 and a 1, I have an 1/8. So this would be 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, and 7/8. And then some rulers, for example, this ruler, go down even smaller. So I have a 1/2, a 1/4, an 1/8, and a 1/16. Oh, I'm trying to show you guys and I'm not even on there. So do you see that? Like, so there's the 1/2, and then the 1/4, and then the 1/8, and then the 1/16. Yeah. So between an 1/8 and a 1, you'd have a 1/16. If this ruler had that mark, it would be like right here, and it would be 1/16. And so you'd have 1/16, 2/16, then in between 3, 4/16. So the littlest marks would be then 16ths. And so when we're measuring with inches, we can't just say, you know, when we hit here, it's not like 2.2 or 1.2 because this line is not a 0.2. This is a 1/4.
Could you say 2.25?
You could convert the fraction into a decimal. Yeah. So for here we're pretty even. We're 4 inches. Here we're at 2, and then we're at 3/4. So you can say 2 3/4, or if you know the decimal for 3/4, it would be 2.75. I've got 1.5, or if you know the decimal, it's 1.5. And then here is 3 7/8. Anybody know that decimal?
I think if you were ready, it'd be 2.33333.
No, it's even. You do 7 divided by 8, 875. So it would be 3.875. So sometimes just having the fraction is easier, especially if you get to like 11/16. Just write 11/16, you know. Okay, so if we're going to do the dollar bill in inches, just like on the centimeter side where the 0 didn't line up, the inch side doesn't line up either. So you have to make sure to line up to the 0 and not the end of the ruler. And if you can see that, 1/16. So we're at 6 1/16. And I'm drawing all over things. Okay. And that's just easier to write as a fraction than to figure out the decimal. And our pencil stop writing. Our pencil can't see it. So there's a quarter, and then we've got two more lines, so that's eighths. So that would be 1, 2, 3 eighths. So 6 3/8. Okay, any questions on? Remember I told you yesterday postulates were statements that were accepted as true without proof? There's actually something called the segment addition postulate, which tells me that I can take two segments and I can add them together, and that length equals the length of the segment that they make. Which is one of those things that you go, well, yeah, if I take two things and I add them together, it equals the big thing, right? That's why it's a postulate. You don't really have to prove it. It just makes sense. So using that information, I want to find EG. EG is the whole length. So it would make sense that the length of this piece plus the length of this piece added together will make the length of the whole thing. Yes? Okay, I have 2 3/4 inches plus 5 1/2 inches, and I want to find out the total length, and here's where I have a problem. Yeah. Yeah, we have to make them the same. So I'm going to multiply this one by what? So I'm going to get 2 3/4 plus 5 2/4, which is going to give me 7 5/4. Am I done? Because that's improper. Well, yeah. 7 5/4 is the same thing as 7 5/4 is 1 1/4, right? So that's 8 1/4. And does anybody need me to do like a lesson on going from improper to mixed numbers and all that stuff? Are you guys comfortable with that? Because if you're not, it's totally understandable. All right, so we've got 8 1/4 inches. The decimal part's easier. We don't have to convert anything. So 4 9 is 13, carry my 1, 8 4 is 12, carry my decimal down, I get 12.3 centimeters. If you have segment addition, you have segment subtraction. It's the same thing. If the whole thing is 13.2 and this small piece is 5.8, I can find out this small piece, I just subtract. So 13.2 minus 5.8. So 7.4 centimeters. Same with the fractions. The whole thing is 13 3/4. And I'm going to subtract 6 3/8. And I can't subtract that yet, so I'm going to make this into eighths, which is going to create it to be 6/8 minus 6 3/8. 6/8 minus 3/8 is 3/8, and 13 minus 6 is 7, and that's feet. Now, if this fraction was smaller than that fraction, if it was the other way around, what if it was 13, here, let's do this, 13 3/8 minus 6 3/4, and then I converted it. Do you guys know what to do with that?
Have to take a whole number and convert it to a fraction.
Yeah. Does everybody comfortable with the borrowing in fractions? Or would anybody like to see this? Yeah, I'd be happy to. What I do is I borrow 1 from the 13 and make that a 12. Well, because I borrowed 1, I take whatever that denominator is and add it to the numerator. Because when I borrowed 1, what I borrowed was 8/8. Does that make sense? A whole, yeah, I borrowed 1 whole. And so no matter what denominator this is, it would be 8/8, or if it was fifths, it would be 5/5, or 7/7, or 11/11. Yeah. So I add this number to the numerator. So instead of being 13 and 3/8, this is now 12 and 11/8. 8 plus 3 is 11. Minus 6 and 6/8. 11 minus 6 is 5. 12 minus 6 is 6. So if you borrow 1, you just add the denominator to the numerator. Good? Anybody need to see another one? Yeah, okay. Let's do 7 and... Okay, so 2/5, I can't subtract the 4/5 from it. So I'm going to borrow 1 from there, making that a 6, and I'm going to add 5 to that, which makes it a 7. So then I'll subtract 7 minus 4 is 3, 6 minus 5 is 1. Okay? Okay, now here's where we throw in some more of the algebra. When you get a sentence like this, we need to convert this sentence into a problem. Okay, I find the value of a and xy if y is between x and z, xy is 3a, xz is 5a minus 4, and yz equals 14. And can you just write that into a math problem right now? It's too confusing, right? Draw a picture. Okay. First, we're going to say, I want to find a and xy. This is what I'm looking for. Okay. So I just underline it because that tells me, okay, this is what I need to find. Then I say, okay, y is between x and z. This is a picture. We're talking about line segments. Y is between x and z. Okay. That's my picture. XY equals 3a. So we use some different colors here to just sort of help. XY equals 3a. This is XY, so that's 3a. And XZ is 5a minus 4. XZ is this whole thing. And finally, I get, bless you, YZ is equal to 14. Now that I have the picture, just looking at the picture, what do I know about this and this together? The equals the big one. The picture helps to put everything into perspective. So 3a plus 14 together equals 5a minus 4. So by drawing the picture, I was able to create the equation. So far, okay? Yeah. Okay. All right, so I'm going to subtract 3a from both sides. So I'm going to get 14 is equal to 2a minus 4. Then I'll add 4 to both sides. and I will get 18 is equal to 2a. I will divide by 2, and that will tell me that a is equal to 9. Here we go, I found a. Remember, I'm supposed to find and xy. So a and xy, so I'm halfway through. xy is 3a. So what I can do is I can plug in that 9 from a, and that tells me that xy is 27, and I found everything. Now, on a problem, let's look at this next one. We're finding x and BC. Terrible underlining. Okay. B is between A and C. So I'm going to draw that. B is between A and C. AC is 4x minus 12, so that's the whole thing. AB is x. Bless you. Bless you. BC is 2x plus 3. And so now we can see that if I add this and this, it'll equal the whole thing. Bless you. Okay. X plus 2x is 3x. Subtract 3x from both sides. Add 12 to both sides. And I get x equals 15. I found x, I still need to find BC. BC is 2x plus 3, so I plug in 15, and I get 30 plus 3, which is 33. Okay, so the word congruent means having the same measure. So congruent segments would be segments with the same length. Okay. The symbol for congruent is a curve over an equal sign. Okay. And a picture of congruent would be to have the same number of hash marks. So I have some line segments. Okay. The ones with the same number of hash marks will be the same length. So granted, I didn't draw these all perfectly, but this picture is telling me that AB is congruent to EF. Okay. And CD is congruent to HG or GH. Now, we talked about, let me just do this over here. That would be line AB. This would be segment AB. So no arrows gives you a segment. And then if you don't have a line, this is the length of AB. So when we talk about, if you talk about AB, I don't have room. I'm going to do this on another page. Okay, I'll come back. If I just say AB like this, with the line over it, I'm talking about the actual segment, like the physical segment. So if this ruler were a segment, I'd be talking about a ruler. Yeah. If I talk about AB without the line on it, I'm talking about the length or the measurement. So this is an actual segment. This is a number. Okay. So in this case is a ruler, right? It's 12 inches. So the ruler itself would be AB with the segment on top of it, the line on top of it. 12 inches would be AB with no line. Does that make sense? Okay. So segments themselves can be congruent. It's the lengths that are equal. Okay, so segments are congruent, length is equal. Okay, so we have xy is 5x, yz is x, and xy is 25. Oh, this one has a typo. This should be xz. Okay, we're going to try to find the value of x and yz. Y is between x and z. So x, y, z. xy is 5x, yz is x, and the whole thing is 25. So in this instance, 5x plus x is going to be 25. So 6x is going to be 25. So I'm going to divide by 6. And I'm going to get x is a decimal. No. I'm just being lazy, to be honest with you. Okay, it's going to be 4.16 repeating, so I'm just going to say 4.17 because the 6's keep repeating forever. So x is going to be 4.17. YZ is equal to x, so that also equals 4.17. For does everybody have this one? Because for the next one I can, oops, too big of an eraser. For the next one I can use the same picture. I can just relabel it because it's the same picture for all of these. Where y is between x and z. So if I come in and I do number 8, same picture, different labels. xy is 4x, yz is 3x, and xz is 42. So 4x plus 3x is 42. So 7x is 42. So x is 6. And yz is 3x, which is 3 times 6, which is 18. All right, when we talk about the congruency, you can have congruent inside one shape, or you can have congruent between two shapes, like segments. The side length, we'll call that our segment. So in this instance, we have AD is congruent to BC. But AB and DC are not congruent because they don't have any marks. We can have two sets of congruent things where you have FG is congruent to, sorry, I'm making the same mistake I told you guys not to make. BH and EF is congruent to GH. 2 marks, 1 mark. Or you can have congruent between two objects. Where I have AB is congruent to EF. And CB is congruent to DE. So even though they're in two different figures, they still have the same number of marks, so that makes them congruent.